We're looking at combination circuits now, basically a combination of series and parallel circuits together. So everything that we've learned already, we're just going to put it all together here. So you don't actually really even need this lesson. You should be able to, just take all the lessons that you've gotten so far in electric circuits and put it together for this. But just in case, I know it is a little bit tricky, so I'm going to help you out there. So first off, as usual, as soon as you have electricity, you can apply Ohm's law. And in this case, we can apply Ohm's law over the battery, which basically means the total of everything, right? So we can use V total equals I total times R total. We can also do across each individual component. Okay, so we can do it for each component, that the potential difference over that component equals the current through that component, multiply the resistance of that component. And then on your note, I've also written that it is sometimes helpful to imagine that the parallel combination of your combination circuit, so the parallel section of your combination circuit, you can imagine that to just be one big resistor. Okay, so for example, for this circuit, we could imagine that this looks like this. We've got one big resistor here, that let's just call it RP for our parallel, and then our little R4 over there. Okay, so we can sort of imagine it as two resistors in series, unless we are asked to do something inside this parallel combination. Okay, so we can also, green, right? Yeah, so we can also do it across the parallel combination. So we can say the potential difference of this whole parallel section equals the current entering the parallel section, so the current coming in over here before it splits, multiplied by the total parallel resistance. Okay, so that's the Ohm's law. And then in terms of, there's always two options. There's always either use Ohm's law or use my understanding of how each of my different physical quantities behave depending on the type of circuit that I have. So we've looked at Ohm's law. Now we're going to look at how the different physical quantities behave. So I'm going to try and leave this here. Let's see if I've got enough space to leave it there. Okay, so we're going to start with current. Okay, so now we're just taking what we know about series and parallel and putting it together. So in the circuit, in the series sections of the circuit, my current is the same as it is in the battery. Okay, so the total current is equal to the current as it is through the series components in this circuit. But then as soon as I get to this parallel section, my current is going to split. And then the current in this branch plus the current in that branch will add up to my total current. Okay, so in general, the total current, remember every time we say total, we just mean what's going through the battery, what's happening with the battery, because the battery tells us about the whole circuit. Okay, so our total current is equal to the current in the series forgot my words, components, the current through the series components of the circuit, which is also equal to the current through the parallel, again, parts. Whoa, sorry. No, it's gone. I've lost the word now. Okay, so the current through the series parts, and then that's also equal to the current through the parallel parts. Okay, but if we consider it as the current moving through our imaginary parallel resistor. So if we broke these resistors, this parallel combination of resistors, up into one big resistor, the current entering this would be the same as the current through there. Okay, but now if we actually look inside there, okay, if we look into this parallel resistor and we actually look what's happening inside there, we've got two branches. Okay, now I have labeled them on your notes. Branch 1 on the left. Okay, so this is branch 1 on your note, that's branch 2. Okay, so our total currents can also then be split into the current through branch 1 plus the current through branch 2. Okay, so that's in general. Now if we zoom in on this parallel section, Okay, we obviously know, we've written it here, we know that the current splits, right? It comes into the parallel section and then it splits. It goes some of it up into branch 1, some of it into branch 2. Now, if we were interested in just what's going on in the individual branches, we could talk about the fact that the current in branch 1 is equal to the current going through resistor 3, and that the current in branch 2 is equal to the current going through resistor 1, which is equal to the current going through resistor 2 because resistors 1 and 2 are in series with each other. Okay, so you need to look at your scenario and break it down the way I have here. Okay, it's not always going to be exactly the same. You need to use your understanding of series versus parallel circuits. What is always true, let me actually highlight that for you on here. What is always true is that the total current is equal to the series current is equal to the parallel current. Okay, and then you need to break up your parallel currents depending on how many branches there are, and you need to break up the current in each branch depending on how the resistors look in each branch. Okay, so that's currents done. Next up, potential difference. Okay, so with potential difference, again, we're using the fact that we know how potential difference works in parallel circuits. We know how it works in series circuits, so we just have to say, well, what will it look like in a combination circuit? So in the series part of our circuit, the total potential difference, the terminal potential difference of the battery is equal to the sum of the series potential differences, right? So it's V series plus the potential difference of this, if we imagine it as one big resistor. So we're going to say the potential difference, the total potential difference, is equal to the series potential difference plus the parallel potential difference. This is always true. Okay, then you'll have to break that up depending on what your scenario looks like. Okay, so this is true always, this is just in general. Then in this specific scenario, we know that the V parallel is equal to, now you know this from parallel circuits, the parallel potential difference is equal to the potential difference of each branch. Remember that. Potential difference in each branch is the same, and it's equal to the total potential difference of a parallel circuit. So in this case, of the parallel combination in the circuits. So V parallel here is equal to the potential difference in branch 1, which is equal to the potential difference in branch 2. Now this is also always true, but you would have to continue depending on how many branches you have. And now we can break this up even further, okay? The potential difference in branch 1. In branch 1, I only have one resistor. Remember what potential difference is? It's basically the work done per unit charge, eh? The energy that the electrons have. So the potential difference of this branch, if this resistor is the only component in that branch, that means it's the only thing that is using up energy. So whatever the potential difference is of this branch, that's going to be what the potential difference is of that resistor. Okay, but now if we look at branch 2, it's a little bit different because in branch 2 I have two resistors and those resistors are in series. Now remember, potential difference in series gets divided. So the potential difference in branch 2 here is going to be equal to the potential difference of resistor 1 plus that of resistor 2 because these are in series. Okay. Yeah, and that's it for potential difference. Then last one, resistance. Okay, so resistance calculation looks very similar to the potential difference one in that the total resistance equals the parallel resistance plus the series resistance. Okay, now this gets a little bit tricky because the parallel resistance, remember, that 1 over R parallel equals 1 over R 1 plus, etc., etc. You do the 1 over thing. So when you take this, which is always true, and you expand it for your specific circuit, so expanding for our specific circuit here, this would be R total equals, I'm going to leave a gap for R parallel. R series, this is R4, right? That's the only resistor in series. Now my parallel combination, I've got two branches. Okay, so for each branch, I need a fraction. So it's going to be 1 over the resistance of branch 1 plus 1 over the resistance of branch 2. And then that will give us 1 over RP. I don't want 1 over RP, I want RP. So remember, we raised this to the -1. Do you remember that? I hope you remember that. Okay, and now we're going to have to expand this even further because branch 2 consists of 2 resistors. So we would expand this to RT equals 1 over resistor 3 plus 1 over, now in branch 2 I have 2 resistors in series. When resistors are in series you just add them together, so that branch would be R1 plus R2 to the -1 and then plus R4, and here you could put in your values and just chuck it in your calculator. Okay, I know this looks terrifying, but you are going to have to do this quite a lot, okay, this section here. So always just start like this, I know it's R parallel plus R series, and then you expand R parallel according to how many branches there are, 1 fraction for each branch, and then depending on if in your branches you have series resistors, you then have to include all of those terms in the denominator for that branch. Okay, pretty sure in the example we're going to do this one like that. So I'm going to pause you, erase this, and we will apply all of it in the example. Okay guys, so here's our example. I know the diagram looks a little bit confusing. Okay, so the blue is the actual circuit. We've got a cell, we've also got a switch, but the switch has nothing to do with the question, so don't panic about it. So we've got a cell, we've got a switch, then our wire splits into 2 branches, so we've got 2 parallel bulbs. Okay, comes back together and we have 1 bulb in series. Then we've got a voltmeter across our battery, V1. We've got a voltmeter across bulb 2, which is V2. And we've got a voltmeter across bulb 3, which is V3. And then this series bulb is called bulb 1. Then above your diagram in your worksheet, they've also given you, or on your note rather, sorry, they've also given you a bunch of information. That's what I filled in green. So they've told us that the reading on V1, or the terminal potential difference for this circuit, is 20 volts. They told us that the total resistance is 4 ohms. They told us that the reading on V2 is 10 volts. And then they've told us that the resistance of bulb 2 and bulb 3 is R and 2R respectively. So we don't know what the resistance is, but we know that the resistance of bulb 3 is twice that of bulb 2. Okay. Then question 1 says to determine the current through the battery. So as usual, we check of the 2 options which can we use. So can we use Ohm's law? To use Ohm's law, I need to know 2 of the 3 variables. Okay, so Ohm's law is V equals IR. I'm looking for I, so do I have V and R? I know the total potential difference and I know the total resistance. So I can use Ohm's law here. I can say V total equals I total times R total, and we can substitute in. So the total potential difference is 20. Sorry, I'm actually just going to put my phone on vibrate. This is annoying.